So, morning everyone. Not so sunny today, not from my room anyway. Okay, so we just checking everything's working okay as far as I can see. Good morning, Don. Thank you. Right, so at the last lecture we went a bit through field effect transistors, and we looked at different types, different flavors of field effect transistor, and looked at enhancement and depletion and all this kind of stuff, and it was all looking a bit scary. And then I've sort of hinted that we need a model for this, so a mathematical model to describe how these transistors work. But fortunately for us, one model will do for all the different types of transistor that we've talked about, and all we have to do is just change a few of the signs of the various parameters. So we got an idea that the output characteristics of this field effect transistor is similar to a bipolar in many ways, in so much that there's a flat region, which is a constant current source region, where the current is then controlled by a gate voltage, but it's not worrying too much about what the supply is over the device itself. So this is what makes it a current source, that the current is constant for whatever supply voltage you put across the device. Okay, and then we've got this other region here, which is a bit bigger than in the bipolar, and has some interesting characteristics which we can look at and maybe try and exploit. And what we'd like to do is come up with a sort of ideally a simple model that explains how this device works under all conditions, ideally. But you can probably imagine that what we can start to do is split this into two types of model. We can have a model for this bit, and we can have a model for this bit, because it's unlikely that in one circuit we're going to want the device to operate in all of these regions. We're going to either have it operating in here, or it's going to be designed to operate here. So we can actually just simplify our model accordingly, depending on the application going forward. But it's good to understand where this model comes from anyway. So that was the output side of it. The input side of it has a curve that looks like this. We don't really know much of the nature of this curve yet, but we know that it does this. And these are the range where these things can occur. They're the same shape, they're just moved in offset, if you like, right, at lateral offset. And there was a special case for a JFET where it will come up here and it would be stopped basically at this point here, and we wouldn't really worry about what's going on beyond this point. But you can see that's just a special case of this depletion device. So this is what we're trying to describe on the input side, and the previous slide was what we want to try and describe on the output side. So we've got these cut-off threshold voltages where if you go below that voltage, the device is off. So that's the important things to worry about there. So we can compare this with our old bipolar devices that we looked at, our NPNs and our PNP transistors. So these are the curves for the bipolar transistor. So this was our input curve, so VBE respect to IC, so remember there's a factor of beta in here, and you can see that VBE, small value of input voltage, controls a large value of output current, and we had this exponential rise going on, and the output characteristics there looks like a very large or wide flat area on the output side, and this region here, which was much sharper in terms of its, or narrower if you like, in its use. And so we tended, and I think is generally the case in all cases I've seen anyway, where we assume that we're going to operate in the transistor in this flat region here, and we're not really very interested at all in what's going on here, because it's just not, it's exponential and steep and not very interesting to us. However, for the FET, it's not quite so steep, and there may be something that we can do in here. So just bear that in mind as we go forward. So this is the bit that we've done in the past for amplifiers, and so that's where we want to bias our FET if we want to do amplification on it. Right, so region 1, this bit here, is much smaller in a bipolar device, and it's typically less than 0.3 of a volt in width. It's going to be more than that in the FET, and these equations we're going to develop will allow us to work out how much more. The usual parameter is IB, the base current in a bipolar transistor, because there's a nice linear relationship between IB and IC, depending on beta. But for FETs, the only thing you can really play with is the voltage at the gate, because it's a reverse bias diode and there's no current. So ideally, there will be no current at all flowing into, or indeed out of, the gate of a FET. So we don't have this equivalence of IB. There is no IB or IG, if you like, in a FET. We've only got gate voltage to play with. So that's the equivalent, if we want to go right back to our bipolar, to looking at VBE on the bipolar. So there's a rough equivalence between that. But remember, there isn't a linear relationship between VBE and IB. It's a non-linear relationship, which we got from that curve that we just looked at. So for a bipolar, the collector current versus input voltage characteristic is exponential and very steep, as we've just seen on the previous slide. And the FET is a quadratic, as we shall find out, and much less steep. Therefore, we can deduce that the gain of the FET, the transconductance anyway, is much less than for the bipolar, so it's not going to have the same kind of gain characteristics. Similar, but not as good. So the bipolar will be an enhancement type in FET terms, if we want to carry on the comparison. And as I've said before, negligible gate current flows for FETs. Because it's either insulating, if we go back to its construction, it was just a piece of glass on the gate, or it's a reverse bias diode, and the current through a reverse bias diode is negligible, ideally zero, but there's going to be a small amount of current. And note the differential terminology for saturation for the two types of device, and I'll comment on that shortly, because it was different engineers who were developing FETs and those developing bipolars. When they came to naming the various regions, they got a bit confused and didn't use the same words. And in fact, they used the same word but for different applications. But I'll flag that up in a minute. So, mathematical description. In region 1, that's this bit here, slopey bit, we've got this equation. Okay, so ID, the current that we're going to get through our device, is given to us by some constant multiplied by VDS, okay, which is this variable here. So this is the supply voltage of the device. Hence, we're going to get a relationship between the current and the supply voltage in this region here. Hence, we've got a rising line. And it's defined by VGS, which is the controlling voltage, the gate voltage, minus VT, so how far it is above the threshold, which is the cutoff voltage. So this is, how far on it's on, minus VDS over 2. Okay, so we don't need to particularly worry where this equation's come from. It's a very complicated thing to develop. There's a lot more to it. There's a whole lot of other terms that are on the end of it, but this is the fundamental term of it. But one thing we can tell by looking at this equation is that it's a quadratic, because we're going to have a VDS times a VDS. So that's going to be VDS squared. And VDS is the independent variable. So we're going to have some kind of x, if you like, x squared, y equals x squared plus x plus constant type of relationship here, if we expand this out a little bit. And notice we have two parameters that describe this FET. We've got k, which is a constant, which we'll look into, and we've also got VT, which we know is defined by the manufacturing and tells us what voltage the channel becomes pinched off at. Okay, so for no voltage in. So this is the cutoff voltage of the particular transistor, and they're the only two variables in this equation. Parameters that we are interested in. Everything else is just defined by the circuit conditions around it in terms of the various voltages applied to it. And then these are just mathematical definitions that say it only operates in this region here, and because it's quadratic, you'd expect it to ramp over on itself. So we're really saying it's only going to be operational up to the first turning point, or the turning point, and after that it doesn't really apply anymore. Not for practical purposes anyway. And region 1 is called the linear region. this region here, is the linear region. And what some of you might then say is, well, hang on a minute, it's not very linear. You know, common sense tells us that this bit is the linear region. But no, when we come to define FETs, people who invented them, decided that this was a linear region. So there's an easy rule of thumb that if you look at the output characteristics for a FET and someone asks you to label it, just remember that the linear region isn't the linear region. The non-linear region is what's called the linear region from a naive view. Okay. Now it's called the linear region because you can see that if you looked in at this bit down here, you would see that you could approximate at least this part of the curve with a straight line, and the slope of that straight line can vary depending on what control voltage we've applied to it. So here we've got a narrow slope, and then for this curve here we've got a steeper slope. And if you have a linear relationship between current and voltage, that has dimensions of resistance, and so this becomes a resistance. If you go up and down a straight line on a VI curve and it's straight, that's a resistance value. The gradient is related to the resistance. So here, if you see, we can change the gradient at this point here. We can change the resistance, and we're controlling the resistance, if you like, of this by a control voltage on the gate. So that's why it's called linear. Right. Vt is called threshold voltage, we know that. K has dimensions A over V squared, amps per square volts, and is called, imaginatively, the device constant of the device. And depending on which area you happen to be working in, if you're in semiconductor physics, you might call that different values. For a MOSFET, people can either call it Kp or Kn, depending on the flavour of MOSFET you've got. For a JFET, parameter is sometimes called beta. And again, it's not the same beta as we had for the bipolar transistor. It's just different people working in different areas at the same time and not really talking to each other. So there's a lot of historical issues in terms of the notation of these things, particularly if you're new into the game. And occasionally you might see K dashed being used for either device, which is actually the equivalent of K over 2 in terms of numbers. But so if you're looking at definitions of the maths for this in different books or different sources, you just have to be aware of which particular version of K they've decided to call K. Alright, so it gets a bit confusing. But don't worry about it too much, because once we've gone past this basics of understanding there is a K, whatever it might be, we don't really use it after that in this course at all. But if you're designing transistors on an integrated circuit at some point in your life, then you will be a lot more interested in which value of K you've actually got, which definition of K you've actually got. So we will avoid using the term beta in this context to remove the possibility of confusion with bipolar transistors. Okay, so having introduced it and confused you, I'm now going to take it away again. So, in region 2, so beyond pinch-off, in the, I call it the flat region, because we're not allowed to call it the linear region now. Okay, we have this expression, same K, again K over 2, so you can see maybe where the definition of K over 2 might come from. VGS minus VT. So this is entirely dependent on the control gate voltage. This is the difference between the control gate voltage and the zero voltage for turning it off. That's all that is. And in this graph here, we're graphing VDS against ID, and there is no VDS in this equation. And that's why it's a straight line. As far as this graph is concerned, this is just a constant. But we can change VGS, which means that we just get a different value of constant. Okay, and then there's some mathematical stuff here that tells us officially where it's valid, but it's really valid after the turning point of the other equation, and has to be continuous with the other equation. They've got to join together. So this is quadratic rise to the turning point until it's flat, and then it just holds that value effectively. Same constants as you'd expect, because it's the same device. And region 2 is called the saturation region. So this bit here is the saturation region. Now remember, in the bipolar, the equivalent of region 1 was called the saturation region. So, we've got a confusion, an instant confusion in terms of definitions of what these spaces are called, depending on if you're talking about bipolar transistors or if you're talking about FETs. So we've got, for this field effect transistor, we've got saturation region here, the flat region, and then we've got the what was it called, the active or linear region here, wasn't it? So this is the linear region for a FET, and it's called saturation in a bipolar, and this is the saturation region for a FET, which is called the active region in the bipolar. So these kind of things make good exam questions. They're kind of definitions. Yes, not quite exactly sure what that symbol is, but I agree with you. Wasn't my idea. There you go, just history. So, if we talk about JFETs, remember JFETs were a special case, and these definitions apply. That BGS has to be negative, and B gate drain has to be also less than 0, otherwise we'll get conduction through the gate. It will be a forward bias diode rather than a reverse bias diode, but that's just saying we can't cross the line. So if you find this all confusing, which looks like Mr. Avishka does, you are not alone. So SPICE, which is a circuit simulation package, is notorious for having difficulty in achieving convergence with FET circuits. So achieving convergence means getting an answer in sort of mathematical terms. Right, let's have a look at a practical device, see what's going on. So all these devices have very imaginative names. So there's a 2N3819, name that trips off the tongue. It's a sort of a very common N-channel JFET, comes in a little tin package, 3 legs on it, and it would have typical measured characteristics such as this, which you can get from the device's data sheets. All devices have a data sheet, which is all the information that you might need to design with it, and gives you all the key parameters and tells you, how much variation there is from device to device. So this is a simplified version. So we've taken this from the data sheet, and you can see that ID, the maximum ID we get for this JFET is when the gate is at 0, and so it's about 10 milliamps or so. So we're not talking about a power device here. This is small amounts of current. And the threshold voltage when the device is cut off from here is minus 3.5 volts. So we're talking about sort of logic level sort of device really. So minus 3.5 volts on the gate will turn it off. 0 volts on the gate will turn it on to its maximum, and that will give us 10 milliamps of current, and then in between we've got these various different characteristics. And this has been done with the VDS, so a supply voltage of 5 volts. Just to give you an idea of what's going on, just sort of typical small values. And this is what its data sheet might look like. And the data sheet will give you a bit of a summary of what a device is, and eventually you'll get very used to reading the detail of these data sheets and looking for the things that they don't tell you or don't want you to get away with, because they're almost like advertising and marketing as well. They're trying to get you to buy this device, so they'll try and talk it up. So this is an N-channel RF amplifier device, the 2N3819. Operates up to 450 megahertz, and for analog switching, requiring low capacitance. So we'll talk about analog switching probably in the next lecture, and we can see why low capacitance might be important there. And if you're interested, it's sourced from Process 50, which you'd have to be a detailed, knowledgeable person about Fairchild to understand what Process 50 means. It's just the technique they've used for making it. And then it gives us a whole load of maximum ratings for various parameters, some of which we may have come across and others we might not know about so much. And these are ones that it will survive to. And it's not necessarily going to operate at these levels, but if you put these levels on it, it won't kill it. So drain gate voltage, 25 volts or so. Gate source voltage minus 25 volts. The drain current, the maximum it can supply or can survive, is 50, which is important if you're looking at short circuit problems. And forward gate current, 10 milliamps. Now remember that we in an ideal world we would never have forward gate current on any of these devices because we want to operate it in the reverse direction. If we have an inductance or capacitance on the gate of the FET, does it get transferred to drain? I don't understand your question, but if you just wait until we start putting device components onto this device, maybe that'll answer it for you. Okay, so the forward gate current, if we set this up right, we wouldn't have any forward gate current. We'd have reverse gate current, and it'd be very, very small because it's a reverse bias diode. But if we made a mistake and forward biased the gate, it would survive up to 10 milliamps of forward current before we'd have to get another one out of the box and replace it. So that's if you make a mistake. It's a bit forgiving, and you can store it against these temperatures. And then there's a whole load of typical parameters that you get for these devices. So the gate source breakdown voltage doesn't sound good, but that's 25 volts, so we stay away from that. Gate reverse current, so this is the current that comes out of the gate if it's reverse biased. You can see that's 2 nanoamps, so that's negligible really. Gate source cutoff voltage, 8 volts or so. Gate source voltage minus 7.5 volts. And it says spot the error. So this is a data sheet for a device that's been around for many, many years, and they've updated this data sheet many, many times over that lifetime. And you can see there's still a mistake in it because this should be minus 8. Okay, so you've got to be careful with some of these things as well. And for the JFET, we know that IDSSS is the maximum current that we're interested in, and you can see here that it could be anywhere between 2 and 20 milliamps. So again, it's not a particularly well defined parameter. There is a typical column here, which a lot of devices will use, and that's one that they can say that most of them have that value. In this case, no one's putting anything in the typical column because this process 50 is obviously so dodgy and variable that it creates all kinds of variability within the devices themselves. So again, just be aware of these things. So this is just a brief introduction to a data sheet. As you go through your university career and as you go through your working careers as well, you'll get a lot more knowledgeable about what some of these other parameters actually mean and whether or not they're going to be important to you in a particular design or not. A lot of these parameters, particularly ones involving capacitance, only really become important at radio frequencies, up say at 450 megahertz or so. That's when they start to become significant in the device, and that's quite a specialist area. Right, so note that the data book gives the threshold voltage, or VGS off, but it hasn't given us K. In this sheet here, there's no value of K for this JFET, and we've already said that K is quite an important parameter. So historically, for JFETs, for some reason they don't give you that value. But what you are given is something called IDSS, and IDSS is the maximum current through the device, and it's defined when the gate voltage is at 0. And this can't be defined for an enhancement device. If you look at the graphs, it'll be obvious why. But it only really applies to JFETs. So how do we get K? So we go back to our equation for region 2, the flat region, not the linear region, and we've got that equation there. And we can start to make substitutions. So we know that when ID equals IDSSS, that VGS equals 0. So all we've done is change this to IDSSS, and we've defined this as being 0. And that gives us this equation here, which then becomes KVT squared over 2. And from that, you can obviously then calculate K from what's given in the data sheet. And so for this device, IDSS was given as 10 milliamps. VT was given as typically 3.5 volts, so we can calculate K from that it's being 1.6 milliamps per square volt. Okay. Numbers taken as average from datasheets, and these are the ones that are used by the SPICE model. So if you want to model this in SPICE, these are the values that will be used inside the model given to you. But we have to bear in mind that given that there was a variation of 2 milliamps to 20 milliamps for IDSSS on the datasheet, and I can't remember what the variation on VT was, but there'll be an equal variation. We've got a whole possible range of values of K depending on what day the device was made and where it was on the wafer and all this kind of stuff. But nevertheless, it's the best we can do, and we've also seen, maybe from if we think back to some of the work we did with bipolar transistors, that this concept of feedback allows us to stabilize devices against parameter variation, and with outside parameters, outside components, we can start to get some control over these parameters as long as they're big enough to be have the effect in the feedback, and we'll talk about that a lot as we go forward as well. So, bit of a digression from maths to simulation. Why do we simulate? As will become increasingly apparent, and this should be ringing alarm bells for you now, the mathematical treatment of FET circuits is complicated and difficult. Oh dear, I hear you say. I thought it was bad enough already. But modern IC designs require millions and sometimes billions of these devices. And so trying to solve this all by hand, particularly as the solutions start getting a bit more complicated, we have to use simulation, obviously. So we have to trust that the model of our device is accurate, because if we're going to trust a computer to design a chip that's going to cost us a lot of money, and it's going to have millions and millions of these devices in them, the model of that device better be right. Right, so SPICE, a bit of history on SPICE. Originally developed by University of California, is still the standard simulation tool for design several circuits. And what's interesting about it is the code that was originally written for it is still effectively being used now. Although you would have thought they could have come up with a better abbreviation for it. Simulation Program for Integrated Circuit Emphasis. Well, they were doing all right until they got to emphasis, I think, but there you go. It's SPICE, that's what we know it as. So originally the code was written in Fortran, and you may not even have heard of Fortran, formula translation, which was a programming language that was very big in the early days, before C even, but very similar to sort of C, but it all compiles down to machine code. No graphics in those days, so it's text input and output only, and this is still the core of all SPICE programs now. And all that's happened is people have written pretty graphical front ends to go on top of this original code to allow us to draw pictures rather than type text in. So, that's come out very well, has it? This was a circuit originally. Something horrible has happened to it in translation somewhere. A new version of PowerPoint since last year. But you can imagine, we have to imagine what this looks like. Well, in fact, perhaps we don't even have to worry about this. I'll come back to this. What I've actually done is, you will find that on the Blackboard on the recordings site, there is another video, bonus video, on a live demonstration of SPICE, how to test a bipolar circuit. So if you want to have an idea of how to use SPICE, if you haven't done it already, then go and have a look at that video, because I step you through the start of this thing all the way through. So I think all we're doing here is we're applying a voltage in here. Let's see if I can sketch it in. There's a good chance I'll get this wrong though. So this is a FET symbol. And basically we're just doing this, I think, because it's all in control of sources. So we're just wiring up a FET. Sam, the clue's in the name. LT stands for Linear Technology, which is the name of the company that puts it on their website. and spice is spice. All spices are the same. You can even use things like multisim, which is on the departmental computers. They're solving the same questions. They might have slightly different ways of inputting information, but it's going to be the same kind of idea. Drawing a schematic, choosing the right devices, and then running the various types of simulation. They should all give you. They will all give you the same answer, because if they don't, they're not much point having them. They're giving you the same answers as if you built a circuit. That's what I'm aiming for. So any type of circuit simulator, I will refer to as SPICE. You can see it here in this slide here. I'm referring to PSpice, which does date this a little bit, because I don't think PSpice is available anymore. But it's still just SPICE, and it's still exactly the same. So LT-SPICE, PSpice, any other SPICE you can come across. Texas Instruments have their own version. I think they call it TINA for some reason. And multisim as well. Yeah, have a look at the question. Have a look at the videos before doing the question, and it'll all be good. Right, so there we go. So this is now in LT-SPICE actually. So testing the 2N3819. So you set up the example. So we've put in the device. We've put in a source. Squiggly bracket means that it's a variable that we can change. So what we're really saying is that there's a parameter in here called VGS, and SPICE will look somewhere to find out what number to put in here, like a sort of variable, and it's actually hidden in this command here, which is LT-SPICE allows you to put commands straight onto the text. You just drop them straight on. Anything with a dot in front of it is an LT-SPICE command. So this is telling it when it runs the simulation, it will step the parameter VGS. So it looks on the circuit and finds, oh, here's VGS in curly brackets. So then it says, okay, every time I run this simulation, and it's been defined that it's going to run it 3 times here because of the three values. First time it runs it, it'll run it with VGS equals 0, and then give us the answer. It'll then run it again without us asking it with VGS equals -3. Oh, sorry, yes, it's not a list, it's a step, so it's going to go from 0 to -3 in steps of -0.5. So it would run it at 0, -0.5, -1, -1.5, -2, 2.5. So however many, that's 9 is it? 2 for 6. It's going to run it 6 times with different values of VGS here, and we should then be able to investigate this circuit and figure out what else is happening elsewhere. What we're also going to do is we're going to, for a DC sweep, this is a command for a DC sweep, so you just have to play with it to work out what's going on here. We're going to say V2, which is this one over here, we're going to vary from 0 to 10 volts in 0.1 steps. So every time it does a simulation, it's going to set VGS to be one value, and then it's going to run voltage 2 from 0 to 10 volts in 0.1 steps. So it'll ramp this voltage up, taking readings all the way, and then it will change this one to the next step here, which is -0.5, put 0.5 on here, and then run this source V2 up from 0 to 10 volts. So it's doing quite a complicated simulation, but and these are the only commands you need to make it do that. So as long as you know what you're doing, it's quite straightforward. And this is just the way that you set these sweeps up. So the commands that we saw on the screen there, these bits here, are coming from these windows that you can put stuff into. So you can just tell it you want to sweep source V2. So sweep means change. In a linear sweep, I'm going to start it from 0 volts and 10 volts in steps of 0.1. That gives us our DC command here. And then we can add a parameter. Parameters are quite useful in SPICE, and this allows us to just type in the commands that we like and drop that on. So that's how we enter those 2 different types of commands. And then, having done that, you run it, and then you just click on the drain of the FET to plot the current. So you just take your pointer and click on there, and it creates this graph for you. And so every time it's run it, so at VGS equals 0, we get this green line at the bottom, which you might not be able to see, telling that no current comes out, and then we increase to 0.5, 1, 1.5, 2, 2.5 and 3. Oh, sorry, it's the other way around, isn't it? With 0 volts here, we get this current out, and then as we decrease it down, head towards the cutoff voltage, we'll get no current through. So this allows us to create the effectively the transfer characteristic of the FET within SPICE for any device we like, and then we can get into the model of SPICE and tweak its various parameters and see what effect it has. So you can see it's quite a powerful thing. And look, we were expecting 10 milliamps, but it's actually told us we're going to get about 11.8 or something. So there's obviously some variation in the model, but that's okay because we're allowed to have anywhere between 2 and 20 really. So you might be better off assuming that you get 12 out of it really. Anyway, that's what happens. It gives you a good idea of what's going on in the device, and you can plot the characteristics for practical and real devices in SPICE, not just ideal ones. People tend to get taught a lot about the ideal nature of these devices, all devices, but SPICE allows you to both work with ideal devices and also practical devices as well. So it should get pretty close to real world performance. Right, so what you should do, homework this week, simulate a FET or JFET in PSpice or LTSpice. And actually you probably go further. What you should be doing this week is the coursework, which is simulating an NPN as well. So anything you do to get up to speed with the simulator is your friend. If you get good with the simulator, it's going to save you a lot of pain and trouble going forward. So don't put it off, just try. There are lots of online tutorials as well, and it is quite intuitive, but the best way of getting good with the simulator is to use it. Right, so that leads us on to our small signal FET model. So in region 2, which is the flat region, the FETs behave like a voltage controlled current source, just like a bipolar transistor that we had. So we can maybe use the same kind of small signal equivalent circuit. So if you think back to the small signal equivalent circuit that we had, it's for very small signals, and we had this in the bipolar. We really had a current source over here, but we said there were equivalent voltage sources as well. We can do exactly the same thing. We know that the flat region is a constant current source. So here's a constant current source. It's got a value of GM, conductance or transconductance, which we understand, or if we don't, we can revisit the bipolar development of this model, and it's the same kind of idea. It's just a relationship, a constant relationship between an input variable and an output variable, in this case an input voltage and output current, and it's dependent on VGS, so it's a dependent source. VGS is coming in here. We haven't really looked at this bit yet. So we know that the output looks like a current source that's controlled by another voltage somewhere else, dependent current source. And that's great. Now, things become really easy then, because we've said that because there is no current allowed to flow in or out of the gate of a FET, because it's just insulated, it's got an infinite input impedance. And if it's got an infinite impedance, then no current flows into it. So this is it. This is the model. So there's no, remember we had on the bipolar we had a resistor here, R pi. There's no resistor here, it's infinite, or very, very large, so in most cases we can ignore it. So this is our simplified small signal model for a FET. So although FETs look very complicated and they've got lots of maths and things associated with them, if we just start looking at the flat region, this is the model for it. And this is easy to use compared with the bipolar model because there's nothing connected to this terminal here. It's just an open circuit, which is great. I don't have to worry about this resistance. So from complexity we get simplicity, which is good. How large is GM? GM is obviously an important parameter. It's what dictates the performance of this circuit because the output current is related to the input voltage multiplied by this term here. And so for a good amplifier, intuitively we would say we'd like GM to be big, please, because then we get a lot of current for a small change in voltage. So how large is GM? If we think back to our definitions of GM, originally. It's the slope of the input curve, which we can get by doing di by dv. You know, we just with nonlinear, so we have to differentiate this, and we know that this is the equation that describes the flat region, so we can differentiate that, and we end up with something that's actually very simple, k vgs by vt. Because if we differentiate the vg squared, you have to differentiate the vg squared, it just becomes a vg. We can multiply it all out. It's simple differentiation. You can get that. And so again, for a JFET, for example, GM maximum, which is occurring at this point here on the input curve, we can say that VGS equals 0. So we just set that to be equal to 0, and this becomes KVT. And we know what K is. It's 2IDSS over VT squared, and this allows us to calculate a value for GM max based on IDSSS, which remember we get from the datasheet, and VT, which we get from the datasheet. Okay. So it's just a question of using those two basic equations. And remember, there are only two equations that apply to the FETS. There are quite a little bit of remembering, I suppose, but it's not too bad. And this allows us then to calculate GM max for the JFET again, should we wish to do such a thing. And remember that GM is the gain constant of these devices, and we want this to be as big as possible. So for a JFET, the best case for amplification will occur when we're operating at this point here with VGS equals 0, because that gives us the maximum value of GM. Down here, GM is less. Still got a value, but it's the gradient of this slope here, it's steepest at this point. But perhaps we'd like it in terms of ID, so we can make some comparisons with the bipolar transistor. So we can start to make substitutions. If we take GM over K from the previous slide and bolt it in here, we end up with this kind of equation, and we can simplify that down to get GM in proportionality, at least, to how ID is varied. So for a FET, this is where it starts to get a bit more interesting. So if you take this, is what it boils down to, you end up with root 2k ID. GM is proportional to the square root of ID. Yeah. So GM, remember, this is the gain that we're interested in. This relates to the gain of our device, current gain, is now related to the square root of ID, whatever ID it's flowing through it. And for a bipolar, GM was proportional not to the square root, but to linearly proportional to the current here. So this tells us something about how the gain varies with IDC or ID, which remember are certainly in this case was down to our bias conditions. The only thing we were interested in for the bipolar transistor in terms of working out what its gain was, well, what's the static collector current running through it, and that will allow us to then calculate GM. Here it's now related to the square root of that, so the GM is likely to be less for a FET than it is for an equivalent bipolar. This sort of gives you a bit of a clue that they might not be quite so good for amplifiers, because their internal gain constant, this GM, is going to be lower because it's related to the square root of the bias current going through it, not related to the linear version of that. And the reason why that becomes important is because if we then start to put some numbers in, because that was a bit sort of, well, it might not be quite so clear. If we start to put numbers in, typical numbers for our 2A3819, we can then calculate GM from the various things that we've calculated earlier, and we get a GM value of 5.6 millisiemens at 10 milliamps of current going through it. So this is the best it can be. Under the same conditions, same current flowing through it, the bipolar device would have had GM equals IC over KT over Q, which is 10 milliamps for IC, and then 25 millivolts for this constant at room temperature, and that would be 400 millisiemens. So the internal gain of the FET for the same bias currents is a lot less than for the bipolar device, which sort of gives you a clue as to why people maybe prefer bipolar devices for amplifiers, because the internal current gain, if you like, relationship is higher than for an equivalent FET. But so therefore, at the same current then, for 10 milliamps going through it, we will get about 1/100th of the gain with a FET compared to the bipolar. But notice that the relationship is not quite so bad if you had lower currents, and lower currents is not a bad thing because it makes things a bit more efficient. So if you reduced your bias current down to say 0.1 milliamp instead of the 10 milliamps, now the gain of the FET is now 0.56 millisiemens and the bipolar is 4. Now these are not big numbers, but they're not 1/100th of each other now. It's a lot less, and that's because of the relationship that's going forward. So sounds like a bad thing, but actually we can make something with that, because this constant here is not the only story in terms of making the gain of a circuit operate. And we can start to we'll look at that and see how we can maybe get around that deficiency a little bit. So if they're so rubbish though at gain, why does anybody use them? Well, here's some reasons. Lack of input current. So remember, there's no current goes into the gate of this. Makes them useful in very high impedance circuits. So microphones, charge particle detectors, microelectrode signals, piezoelectric sensors, all these things that have a high output impedance. Feeding them into a FET amplifier is really useful, and you find them at in the front end of all oscilloscopes, for example, because you don't want any current going into your oscilloscope when you measure something. But we'll talk about that as well going forward. That's really useful. This is something that you would have to take my word for. They're very linear, makes them useful in the front end of radio receivers where you don't want any distortion, particularly at that point. So that's just something to be aware of. They're very useful as analog series or power switches. So analog switches, transmission gates and stuff, they're really useful for that. You can't use bipolars for that, and we'll talk about those as well. And they are essential for high density CMOS IC design as digital switches. And as I say, there's a lot of efforts gone into developing the processes to make FETs for switching purposes. You don't need high gain for switching. It'd be nice to be able to include them on the same, or include analog circuits on the same substrates. It just makes life much easier. And engineers, being imaginative people, would like to be able to use analog techniques as well as digital techniques on the same piece of silicon. So what we will do now, well not now, but next week probably, is we'll start looking at some examples of FET circuits and how we apply some of this sort of very dry theory that we've just learned, or at least been introduced to. And then that should just make life so much more interesting when we can see how we can actually make all these types of circuit, and how we can briefly analyze them and understand how their performance operates. And after that, once we've got this all sorted out, we can move on after Easter probably to looking at operational amplifiers, which are really useful. And all this is leading up to why op amps are as they are, and allows us to then use op amps to design a lot of mathematical circuits very easily. So that's where it's all heading. It's all good stuff. So I'll see you next week.